What I want to talk about here is elliptical orbits. Now, I've done a pretty crap ellipse, but there we go. Now, you know with the ellipse that there are two foci, or foci, don't know how to say that, but foci, and one is where the Sun would be, and this would be your little satellite going around the orbit. Now, all orbits are a little bit elliptical, and a circle is just a special type of ellipse. Now, what we wanted to look at here is just the energy in the whole thing. Now, we knew that the total energy for a satellite in orbit, see, when you've got the circular orbit, you've got two types of energy. You've got the satellite, it's got kinetic energy, and so we worked out that the kinetic energy was equal to gmm all over 2r. Now that's positive, and that's constant because the r is constant. And we worked out that the potential energy was equal to gmm all over r, but that was negative. So we worked out that the total energy, this is all for circular, was gm little m minus 2r. So the total energy was actually negative. This is all the circular stuff that you should know. If you don't, go and look at my little video on energy and potential energy. That's how we worked out escape velocities and things like that. Now the thing is, the total energy in this ellipse is going to stay the same too. But now we've got this interplay between kinetic and potential. With a circular orbit, they stay the same. So total energy is going to stay the same. We're going to have conservation of angular momentum. All that's going to be at work. Now, when you come down here, looking at that distance compared to the distance here, we can say immediately that the potential energy up this end of the orbit is less. Alright? Sorry, is more. And the potential energy at this end is less. So we can say immediately that the kinetic energy up this end is less, and the kinetic energy up this end is more. So it's going faster. We can say that immediately. It shouldn't surprise us. Now, when we look at the forces in here, we can see that depending where it is, the force is always directly towards the source of the force, which is the planet itself, but no longer is it at a tangent to the velocity vector. So part of the force now is actually acting tangentially, and so either slowing or speeding up that planet, thus changing its kinetic energy and its potential energy, and that acts all the way down. As we go up here, we've got that force. You can see quite clearly that it's not at tangent to the velocity here, and therefore part of the force can be broken into components. We can have a look at this component here. So the force is actually a force like that, right, back towards the planet. That's got two components. It's got a component that is perpendicular to the velocity, and it's got a component that is tangential to the velocity. So this component here is slowing it down, decreasing its kinetic energy, and that's why we've got a low kinetic energy when we get up here. No? But at the same time, the velocity is still that way. So its potential energy is still increasing. So these are the sort of little interplays that are going on in elliptical orbits.